Yeah, I would like to thank Zhui Shen for inviting me to this workshop, celebrating Carl de Boor's 80th birthday. Shen asked me to present a review of Carl de Boor's work. It is beyond my ability to give a full review, so I only just review a part of it, his work, and what I learned from Carl de Boor. This is the main thing, okay? So let's start with B-splines, okay? So B-splines, suppose that is a univariate B-spline. Suppose we have a node sequence, okay? Then not B-spline, polynomial splines, and on each interval, then it is in a polynomial of order k, means degree at most k minus 1. Also, at each node is allowed to be a multiple node. Then you have smoothness, the connection of the lower limit and right limit, left derivative and right derivative. So this is well known. Then we just denote by SKT the space of all splines of order k with not a sequence. Next, now we have B-splines. The B-splines, in fact, was introduced by Curry and Schoenberg in 1947. So we use divided difference, okay? So we have a node sequence, this is a divided difference. This is a truncated power. Then here we adopt that the definition of divided difference from that Carl de Boor, that we defined the case divided difference as the leading coefficient of the polynomial of order k plus 1, which agree with G at these points. So properties of B-splines, so B-splines is compactly supported and has a partition of unity. And more important, B-splines form the basis of the space of splines. So this is a theorem of Curry and Schoenberg in 1966. Probably they just consider finite node sequence, not the bi-infinite node sequence. Now, we have this famous de Boor and Fick's quasi-interpolation. And their approach is different from Curry and Schoenberg. Now, they introduce this, they introduce, let me see, should be this one, yeah. Explicit that dual function, lambda I. So lambda I is explicitly defined. So we have this psi I, this is a polynomial, in fact, this product, then we have the derivative. And now, this is something like a dual argument. When you consider problem, you often go to its dual. Here, often Carl will give us some surprising result, a very short and very elegant. So this quasi-interpolation scheme, yes, is such a thing. And quasi-interpolation scheme made a profound impact on many areas of analysis beyond the spline theory. In fact, I'm going to give another talk on interpolation, quasi-interpolation. And now also in this talk, there will be no new results, but there will be some new stories. That is stories probably you didn't know before. So we have quasi-interpolation and explicitly defined, then this is the dual. Lambda I applied to B-splines, Bj, we have delta Ij, that is chronic symbol. So then it's easy to prove that B-splines form a basis. Okay. Next, let's discuss discrete B-spline. When I was a student of Carl de Boor in 1980, then in the summer he suggested this problem to me to study discrete B-spline. And we here present an outline of univariate B-splines. Now this is also for my own purpose, because after so many years, I could not remember every details. So maybe say start 2 or 3 years from now, I would like to look at say all the references. Then I can go back to this talk. Now this gives an outline of univariate B-splines, but with a different perspective. That is, everything can be done based on discrete B-spline. So discrete B-spline, we have, because B-splines form a basis. So suppose we insert new nodes. Then for this insert new nodes, so S is a subsequent T, means we insert some new nodes into S, we get T. Then for here, then the B-splines with respect to the node sequence S, this is a linear combination of BIKT. Then this coefficient, the sequence of coefficients, this is defined as discrete B-splines. In particular, if we just insert one new node, then it becomes quite simple. And all the others, we can find the discrete B-splines explicit. Now, for j less than I minus 1, all j is bigger than I, all these coefficients will be 0. And then for these two, just a partition and explicitly defined also. If we just insert one new node, this is quite simple. Then if we want to insert more nodes, then just insert one by one. Always you can use induction argument. So as Carl de Boor suggested, I did this in 1980 and published it in 1983. So for total positivity of discrete B-splines, of course, before there's already total positivity for B-spline collocation matrix was already known, okay? But for discrete B-spline, the proof is really quite easy, okay? Now we just insert one node by one node. So we only just consider the case when we just have one new node. Then we have explicit matrix, and this matrix there is total positive, means every minor is non-negative. This can be calculated exactly. So we can use discrete B-spline now further, let's say, to give an easy proof of total positivity of the spline collocation matrix. The idea is that we can relate that the continuous B-spline we just insert the sufficient many, but exact number of nodes. Then this will be can be reduced to discrete B-spline. Okay, so originally this was established by Carl. Okay, but if we use a discrete B-spline, we can give an easy proof. Then in that time, also people were interested in sign changes. Okay, so this is also important in applications of B-splines. Okay. Then we have this something like valuation diminishing. The next page will be valuation diminishing. Okay. So if we have a spline, and here we have, let me say, we have two node sequences. We use this S bar A to denote the sign changes in the sequence of A1, AN. Then suppose let's say S is a refinement of T, means we insert some nodes into S that we get the sequence T. Then we have a spline can be represented as the T B-spline with respect to T, and also a B-spline with respect to S. We look at the sign changes. Then we conclude that the sign changes of the B sequence is no bigger than the sign changes of A sequence. So this can be also, the following proof was given by de Boor and de Boor in 1985. You can see the idea also is about the same. We just insert one new node, okay? If we insert one new node, then we have BI can be represented as this linear combination beta I minus 1 and here alpha I. They are just something like a discrete B-spline, and they are non-negative. So though non-negative, we have sequence A, we just insert B, because BI, the sign is either AI minus 1 AI, so we insert BI plus 1, it will not increase the number of sign changes. Then we remove all this AI, so for sure, we get at least the sign changes of the B sequence. So now from the previous result, we can easily establish valuation diminishing property. So given a function f, we use S by f to denote the number of sign changes of the function f. So the original result was done by Schoenberg and Carlin. So we have this statement. That is, we have a B-spline as a function, not a B-spline, a spline as a function as a linear combination of B-spline. Then its sign changes is no bigger than the sign changes of the A sequence. So this we can also be proved also easily by using the previous result. Okay, we just insert sufficient many new nodes, then we can reduce the problem into the previous one. So this is also related to zeros of splines. Now this is quite, because univariate splines, the theory was developed early in particular, now we mentioned that the talk given by de Boor in 1976, but still about 20 years late, we had this nice result of Goodman. Okay, so Goodman just gives number of zeros of a univariate spline. But this condition is necessary. That is, first we have to define what is the meaning of multiplicity of 0. So here says you have the derivative until the order m minus 1. But you also require that the m's derivative be continuous at that point. Then here we have this condition. This condition is necessary, otherwise it will not be true, okay? For every x in that interval, we have some term with the coefficients non-zero, okay? Then one can prove that the number of zeros is no bigger than the sign changes of the A sequence. Yeah. Now, here I only describe the theoretical aspects of univariate B-spline. And I believe that these zeros and sign changes also have significant meaning in engineering application. Probably somebody will talk about it, okay? Now, how about the proof? Proof also just gives an outline of proof. Suppose x is a 0 of the function in that interval. Then insert nodes, x nodes repeatedly into the node sequence until x and the multiplicity k minus m minus 1. Then at the h is sufficiently small, then insert the nodes in x minus h and x plus h. Each with multiplicity k. The node insertion does not increase the number of sign changes, as we mentioned before. Then we can use the quasi-interpolance of De Boor and Fix to finish the proof. Now, I really like that De Boor and Fix quasi-interpolance. Now, for univariate splines, almost you can use this quasi-interpolance almost to solve any problem. Of course, later this idea was extended to many areas. Here we have the most general result of B-spline collocation matrix. When we have the knot P is strictly increasing, this was, as we mentioned, was done by Schoenberg. Schoenberg. Then when we have multiplicity, now both in the node sequence, also for the nodes, for the zeros, multiple zeros, also maybe multiple nodes. Then this most general result was done by De Boor in 1976. So we have, here we have derivatives to the order mu I. We have what is mu I. Here we have definition of mu I. We use mu I to denote the number of nodes for which Zj equal to Zi. So we have this matrix. This matrix is every this minor is non-negative, but moreover, this gives you a precise condition for this minor to be positive. So just Zi strictly between Tji and Tji plus k. So this theorem, now of course was proved before Goldman's result, but also we can use that zeros of splines to give it a simple proof. Then again for spline interpolation, and this is Schoenberg and Whitney. This is also a well-known result. When the node said that the sequence is strictly increasing, but De Boor's result in 1976 is the most general. Now, this can be derived from the previous theorem. So if we wanted to find a spline such that the spline interpolator at the point Zi interpolate Yi, but also with some derivatives, okay, then it has a unique solutions for arbitrarily right-hand side if and only if Ti is between Zi and Zi plus K. So this gives, yes?
I thought that the ice interpolation point is between the ice and the I plus K not.
It should be the other way, Zi between Ti and Ti plus K. Yeah, this, yes, thank you. So yeah, this was a mistake. So this should be Zi, this should be Ti, this should be Ti plus K. Thank you. Okay, now let's talk about bounds for least square approximation by splines. Yesterday, Xie already gave details of his solutions of the famous de Boor's conjecture. So we can just briefly, now, all the arguments, okay, to prove de Boor's conjecture, firstly, you must know that all these corresponding matrices are total positive. This we just mentioned, okay? We have T is a finite node sequence. Of course, this can be extended to infinity or bi-infinite sequence later. Then LTF is the least squares approximation to F. Now, least square approximation is a linear approximation scheme. But often you would like to estimate your approximation in the L infinite norm. But if you try to do L infinite norm often, would be a non-linear approximation. So if you have linear approximation, it can achieve maybe not the best approximation, but achieve a good approximation. Usually linear scheme is preferable. However, this is the point of view of Carl de Boor, he told me, okay. So if we want that in L infinite norm approximation, but we use least square approximation, whether this still gives us a good approximation in L infinite norm. But this depends on whether this norm that is bounded. Okay. So this is equivalent to saying that the grand matrix GT, depending on the sequence T, so we can write MI is just something K times B-spline divided by the length of the interval. Then this MI in the product MI with BJ, so this matrix is totally positive. Then it should be in 1972, but here say published year is 1973. So Carl de Boor raised the conjecture and also offered prize to solve his conjecture. That is the supreme. Should be the boundary should be independent of the sequence, but of course it must depend on K, the degree, the order of splines. So yesterday already Xie described his solution of de Boor's conjecture. But his original proof is quite long and complicated. A short and simple proof was given by Kolicek recently in 2014. Also, yesterday he mentioned that his theorem was proved only for K complete finite sequence. K complete means at these two endpoints, then the multiplicity is K minus 1, okay. Then there is no reason for any finite section of T to be K complete. So there is still a gap in the proof. Also, it's not clear how the result can be extended to infinity or by infinity knot sequences. These problems were settled by de Boor himself in 2012. And from Scheduling's proof, together with the following lemma, and de Boor attributed this lemma to a joint paper of three of us, okay, with de Boor, Pinks, and with me. But in fact, in that paper is about infinite matrices. But that paper, in fact, did not really give the proof, just mentioned that. So this proof was still given by de Boor himself, but he just attributed to the previous work. Now I think this theorem, this is a recent theorem for de Boor, is quite interesting. And we discussed about this issue, but I did not have time really investigate this problem. That is often this is not just for spline theory. Now we have infinite matrices. And now we would like to know two things. Suppose we have infinite matrices. Then we would like to know whether it's a finite section that infinite matrix is we can interpret as an operator. Then it is bounded. Whether reasonable that the finite section, principal section, something like that, but for infinite matrix, it's hard even to define principle. Whether the section, that submatrix, that minus, they are all bounded. This is one direction. Another direction is, suppose you have the subsection, finite subsection minus a uniformly bounded, whether the infinite matrix is bounded. Here, this theorem is for totally positive matrix. But whether it can be extended to more general matrices. Now, even for Topli's matrix, I often encounter such a problem. Now, we can prove a finite subsection bounded whether the total thing, whole thing is bounded. This is not just for spline, for many problem analysis yeah. So probably, I think in this direction, there is still some interesting research that can be done. Next, okay, let's discuss multivariate splines. Multivariate splines, this part, I basically followed de Boor's talk. The way things were in multivariate splines, a personal view presented in 2009. That is in the conference for Wolfgang Dahlmann's 60th birthday. Yeah. So 80 years ago, 60th birthday. So de Boor gave a personal account of his encounters with multivariate splines during their early history. Now, here de Boor mentioned that how he found a good way to do tensor product of univariate cubic splines interpolation. Now, I knew that this was done in 1960, but in 1970s, de Boor's work, this work in this problem was very popular, okay? Also in China, also in the areas of CGD. Okay. So this is, let's say, use a test product of cubic spline interpolation. And next, this is famous talk at the second Texas conference in 1976. Now, I learned univalue splines mainly from his this talk and in the paper. And but at the end of his talk, he also mentioned briefly that multivariate splines. Okay. That is Schoenberger's multivariate B-splines. Now, in De Boor's own talk, he mentioned that once he discussed with Schoenberger, and Schoenberger just pulled out a letter, that the letter was sent to Phil Davis in 1965. So already constructed bivariate quadratic B-spline. In 1978, Micheli constructed simplex splines and obtained a recurrence formula. And from Micheli's view of Schoenberger's multivariate B-spline, suppose we have a convex body B in Rn and a linear map, then we can define NB B-spline, multivariate B-spline, associated with this convex body B as a distribution. When NB applied to a test function, this is the integral over B of phi composed with P for all test functions. So now, then we have polyhedral splines. Now I arrived in medicine in 1980. So that time, in particular, Hershey with De Boor, also Diamond with Micheli. So they did an extensive study on multivariate splines. So they, in a joint paper of Carl de Boor and Hershey, they call MB polyhedral splines. Then, in particular, the work of Diamond and Micheli, that is, say, we call simplex splines. And Diamond introduced the multivariate truncated powers, which can be regarded as cone splines. Yesterday, Armstrong gave a talk emphasized that the role played by multivariate truncated powers. Then in 1980, at that time I was already in medicine, I met Carl de Boor in that MIC Wolf building, and he gave me a lot of help, okay, in mathematics. So that time the main interest is approximation. The approximation achieved by a space of piecewise polynomials on a partition. Then they suddenly realized that Coulom's head function is the shadow, skewed shadow of 3 cubes. Then some other finite elements also could be obtained as shadows of high dimensional cubes. Now we can say this is in the spirit of Schoenberger's B-spline, okay? Then this motivated them to introduce box spline. Okay. Now, Carl de Boor emphasized several times that box splines were introduced by De Boor and De Boor. But often, many people did not know this. Okay.
Well, it was all Carl.
So when you say people don't know, you
didn't know. When people talk about the box spline, of course, De Boor, Hershey mentioned their book, also Diamond and Micheli. This is most well known, but probably they did not know the contribution made by Carl de Boor in box spline. Yeah. So we have box spline now in Charlie Micheli would like to call cube spline. Maybe cube spline is more appropriate, but we already accept box splines, so we just use box because this is a cube. Okay, if you insist the polyhedral splines, then this should be cube spline. Okay, not just a general box. Okay, so this definition is just we specify that the convex body to be a cube. Then we have its support is the donor-top of induced by these multiple vectors. Okay. Of course, the authoritative work is De Boor, Herlihy, and Riemann on box splines. The influence of box splines and the study of box splines made a profound impact on many areas of mathematics. Box splines are piecewise polynomials, so they provide a powerful tool for approximation and interpolation. Their study led to a comprehensive research on approximation by shift invariant space, scaled shift invariant space. Now, we first have some concrete objects. Then later we try to generalize more and more. Rather than we first have a general result, then we apply to general theory. Now, today we learn functional analysis. Okay, we accept all these big theorems. Then we try to apply functional analysis to Fourier analysis. But in history, we first had Fourier analysis. Then in the study of Fourier analysis, then gradually formulated some general principle. Here again, for shift invariant space, we study box splines, then we study more general shift invariant space. Box splines are refinable. They are suitable for subdivision schemes and wavelet construction. And subdivision schemes play a vital role in computer-aided geometric design. Probably Peter will give a talk about this. And the wavelets induced by box splines are useful for numerical analysis. Now, for computer-aided geometric design, maybe Peter or maybe Tom will talk more about it. So when I discuss with Zhu Weisheng, they say, I'm not so familiar with that. Maybe the other people can talk in more details. Then from their construction, box spline or more general polyhedral splines inherit certain nice algebraic and geometric properties. Indeed, the box splines have found some interesting application in algebra, geometry, and combinatorics. As I mentioned before, I'm going to give a talk on quadratic interpolation, so that related to approximation. So in this talk, in the remaining time, I mainly discuss the algebraic aspects. So we have, for box spline, we have partition of unity. Then we discuss linear independence and locally linear independence. And now these three conditions are equivalent. That time I did it, now this is the year of publication, okay? In fact, maybe 2 or 3 years before, I used the same idea as I did for discrete B-spline. We just insert one vector each time, then I give approval of this result. And then Carl de Boor showed me that Diamond and Micheli already had the results. But he said, okay, now you could still as independent results. So he recommended publication. Also at that time, there's Carl de Boor, there's constructive approximation just newly established. So one paper was accepted. So here now, probably I don't have time to give all the details, but already yesterday in the discussion of Armstrong's work and also Diamond mentioned that. So this is important work of Diamond and Micheli. And in De Boor's, in their three De Boor Hershey and Schneider's book, they noted that if without this important result, probably they would not write that book. So, but here that the dimension of the kernels or joint kernels, okay, is equal to the number of bases in X. It is also equal to the volume of the zonotop. But, yeah.
It's equal to the volume of the zonotop only in the unimodular case.
Only unimodular case? No, I have to record. Thank you for your, yeah, I have to check it again. Okay, thank you. But anyway, now, the volume of the zonotop, this was not a new result, was known before Diamond. You have a zonotop, then you calculate the volumes. So this already was done, I think, before Diamond and Micheli work. Yeah. Now you look at the study on polyhedral and this. So I think, thank you for your correction, okay? But then, I believe that for the volume of the zonotop, it was known before that. But here, for the dimension of joint kernel, this is why it is important, because later development was based on this. So now, approximation, I skip this, and also let me focus on, I think I focus on now some algebraic aspects. Okay. Now for stationary subdivision, I think this was earlier than Debussy and Legari's work. Okay. For stationary subdivision, this is the book AMS Memoir, Cabrera, Diamond, and Micheli. Okay. And also for spline wavelets. Okay. Spline wavelets we use now for univariate that cardinal splines we know that was Chewy and Wang, Jianzhong Wang, Charles Chewy and Jianzhong Wang's work. But Boors splines to construct wavelets in lower dimension from Boors splines and rematerialization work, probably first done by them. Later also, my joint work with Micheli, also De Boor, and Rong. But I would like to emphasize that rematerialization thing in this direction was an early leader in this research. Then dimension of kernel of linear operator. Now, after their paper published in 1985, then in 1990, around 1990, 1989, so there was some new interest. Okay. Now, mainly maybe because of Armstrong, the joint, then University of Wisconsin Medicine. So that time I got a paper of Diamond and Micheli, okay? Then I showed to Zui Seng, say, hey, there is an open problem. This open problem may be quite difficult. You just try. That time I just visited University of Alberta. Then probably in 1 month or so, he solved this. I think it's a difficult conjecture. Anyway, if it's not difficult, probably Dam and Michel already did it. So this is what is the beginning of Zhu Weiseng's work in this direction. And later then, 3 of us, with Riemann, Anderson, and myself, we wrote a paper on dimension of kernels of linear operators using matroid theory and algebraic geometry. Now, this paper was published in a good journal, American Journal of Mathematics. Probably Charlie Michel was the referee. And then there was a workshop organized by Diamond in Oberhofer. As a result, there are 3 or 4 papers. And these 2 papers, one is by de Boor, Rong and Seng, and the other paper by Diamond, Dress, and Micheli. And both papers were selected by math reviews to have featured reviews. But now they don't have featured reviews. Now I was asked to write a featured review for both papers, but this would be too much. I just wrote 1 featured review. Then I said to the editor, maybe you find someone else to write another review. And in the same issue, we have perturbation of polynomial ideas. And this idea I learned from de Boor and Rong. I think now, perturbation of polynomial ideas. Now, this idea was not new, in fact. If you look at, say, algebraic geometry. But I learned from them, still I think there are some problems, interesting problems, we even cannot answer today. Now, if we really can do well in perturbation of polynomial ideas, you can solve many problems. But this is still a difficult problem, okay? But also I want to mention, now this I did not know much about it. Then some of the relatively recent work of Carl de Boor on multivariate interpolation. Okay. Now this mainly polynomial ideas played a vital role in the study of Carl de Boor on multivariate splines. So next, let's discuss magic squares. Okay, magic squares. Then this magic square. Now the number of magic square is a polynomial of degree n minus 1 squared. This was established by Stanley. And Diamond in 98. Probably they did it in 1983, maybe published in 1985 or some 86, something like that. So they established the connection between the linear Diophantine equations and the so-called discrete truncated powers. Using this approach, they succeeded in reproving and extending certain results of Stanley or magic squares. Then, in 1992, I solved Stanley's conjecture on symmetric magic squares, okay, using multivariate discrete sprites. In that talk, de Boor presented in 2009, he mentioned that this result was not recognized by the community of combinatorics. But the situation changed soon. That was 2009. In June 2010, I received a message, email message from Stanley, very friendly message. He asked me for reference because he was doing revision of his book. He even asked me my name, how you write in Chinese characters. And he even asked what is the meaning of my name. I told him my name is Rong. Rong means glory. Qing means celebration. Yeah, celebration. Yeah. So now then I replied to his email message, and these two papers were cited in his revised book on enumerative combinatorics. He acknowledged that that application of B-spline, yes, is significant. You really can solve some difficult problem. Now, the problem itself probably is not that important. But if you can use analysis method to solve a problem, a non-trivial problem in algebra and combinatorics, this is important. Now, we look at the Poincaré conjecture. Why the Poincaré conjecture could be solved? For a long time, if we just use topology to solve a topology problem, it was not successful. So the first step is to introduce richer flow, to use geometry to reduce the problem to differential geometry and a nonlinear partial differential equation. This was mainly done by Hamilton. The next step by Perma, he succeeded in solving this non-linear partial differential equation. So you use analysis method to solve a non-trivial important problem in topology. I think this is what I'm really interested. Okay.
Yeah. Yeah. Did you have a lot of problems getting these papers published?
Yes. No. Finally, I sent my paper to linear algebra application. And again, Michele was the referee.
Oh,
yeah, I guess Michele was the referee. No. First, I sent to this journal and that journal. Now, their reaction, they did not say your proof was wrong. Or they said that your work has no influence. This always is will not have influence. Yeah.
There are several cases of a similar nature where just the response was, oh, this is not important, or that's not
but this was non-conjecture standard.
well,
It's simply
But who says that you can say that the conjecture is not important?
The conjecture itself may be not important.
if you don't,
It's basic if you want.
Even in 1970, Stanley was elected to that what is academia, academic science even earlier than Carl de Boor. Then mainly because of his 1970s
I
work.
had a combinatorist where I was saying that
Alan,
it can't be true, his proof can't be true because it's using different methods.
Alan, you have a conjecture. Person A proved the conjecture, it's an important conjecture. Person B proved the conjecture, it's not important conjecture.
there's a general
I didn't understand that.
communities defend their claim. If you are an outsider getting, you get
That's correctly.
Yeah, if you are not in the circle,
You're an outsider.
if you are outside, you probably it would be very difficult to publish a paper. Everybody knows.
It's very simple.
Yeah, but anyway, you just publish it. In any journal. Why you care? You try to find. Okay, Charlie Michele is not here, but I would like to acknowledge the first influence, of course, Carl de Boor. The second, for sure, is Michele. Okay. The next, okay, I see the situation changed a little bit. Okay, let's go to the final page. Now,
Stanley, he reads, writes, and speaks Chinese.
Uh-huh.
He writes and speaks.
Oh, in Chinese.
Because of that, he wanted to know how you write your name and so on and so
Oh, okay, okay. Now, I thought he wanted to refer the paper in Chinese character, but not. Now, if you have good research, eventually your work will be recognized. But eventually, how long, you never know. So let me finish, because I already probably over time, okay? Now here also I think this is interesting. Now we have recent developments. Yesterday Armstrong also mentioned the recent development. Also say Xu Ziqiang and with Storm affairs used multiple splines to study some problems in geometry, in combinatorics. Okay. Here I mentioned that the book by these two Italian mathematicians, they are algebraists, topics in hyperplane arrangements, polytopes and Boors splines. Okay, so why now? Process, I knew his name, yeah, because I bought a book of his book on Lie groups. Probably this is the I most like books on Lie groups. And also around that time, maybe before, we had some short communications. He asked me about strain fixed conditions, strain fixed theory. Strain fixed theory originally, as presented in their original paper, is incomplete. So I sent some of my papers to them. And in fact, they also included strain fixed theory, but they recognize the community of Boors splines. The Boors spline played an important role in their book. Also, they mentioned, okay, Boors spline, de Boor, also diamond and material theory, also even in the preface, they mentioned my name and cited my two papers. So you can say Boors spline, the influence is beyond the Boors spline. Also, now, who knows what will happen next? Now, why they study, say, Lie groups or the algebra? One main application is in physics. Now, you have standard models. Now I've read some books written by physicists. Now they started probably their knowledge of Lie algebra. I mean, they know much more Lie groups than us. Okay, thank you. I'll stop here.